Hello. Okay, guys, am I live? Can anyone hear me? If you can respond in the chat, that'd be fantastic. Is the chat working? Subscribers only. Okay, brilliant. So today's plan for those who are watching, the four viewers, fantastic. Um, we're going to go over atomic structure, structure and bonding, or quantitative chemistry, which deals with, of course, numbers and moles and masses, empirical formulas, percentage yield, develop inorganic tests. So we'll talk about how do you test for a certain halide ion, for instance, or flame tests. And then finally, organic chemistry. Although, depending on who's here, the four viewers, I imagine that they're all probably not covered by organic chemistry. So yeah, unless you want to stay behind and do organic chemistry. So we'll probably decide in the next 20 minutes or so. But because there's only four viewers, if you could sort of advertise this to your peers, that it's clearly a free stream here, that we're doing an IGCSE Edexcel chemistry stream, that would be fantastic. If you can sort of increase that sub count, that'd be great. And of course, the exam's on Monday, so we need more of a presence. That'd be fantastic. Okay. In fact, I may Control C the link, and then we'll get started at, let's say, 10 past or less, maybe. Okay, let's get started. Atomic structure. Now, I'm going to be very interactive and ask questions on the board. Okay. So the atom consists of three subatomic particles. Can everyone tell me what the subatomic particles may be? Can respond in the chat. The three subatomic particles. We can imagine there's a bit of a delay. The three subatomic particles would be protons, electrons, and neutrons. Of course, neutrons and protons, they're found in the nucleus. And the nucleus, of course, although it shares the same concept, it's in the middle of the cell circle. With cellular nuclei, you've got to appreciate the nucleus is positive. Okay, I'll come to that in a moment. Electrons, these are found on the shells. Okay, the basic stuff. This comes up in physics as well, to be fair. So if I were to draw a table, so this would be, let's say, mass, and this would be charge. So for an electron, typically it's -1, isn't it, as a charge? Protons would be +1, and then neutron, the charge would simply be 0. It's neutral for a reason. Now, the mass for a proton is 1, the mass of a neutron is 1, and the mass of an electron is approximately 1 over 2000. We call it negligible. Okay, rather insignificant, the mass of an electron, because it's so small. Okay, and there's sort of 3 tenets you need to adhere by, 3 sort of principles. And one of the principles is that the mass number, the atomic mass, is simply the addition of protons and neutrons. So the mass of the nucleus, that is. The second principle you need to appreciate and sort of apply in future questions is that the atomic number equals the number of protons. Okay, straightforward stuff, isn't it, really? And then thirdly, third belief, um, the third law in a way, is that the number of electrons equates the number of protons. Okay, so on and so forth. So some basic ideas here. But as you know, GCSE chemistry, IGCSE chemistry is not that straightforward. So before we in fact, let me talk about the plan for today, because obviously those who are now tuning in, we're going over atomic structure, we're going over structure and bonding, and a way to answer a certain question. I sort of call it the SBE format. Also, we'll explore some maths in quantitative chemistry, and in qualitative chemistry, we'll deal with colour tests. And then towards the end, I don't know how many year 11 viewers are tuning in. If they are tuning in, then I will do a segment on organic chemistry. But those who haven't learned organic chemistry, it could benefit you, but in terms of optimizing time, I wouldn't recommend. Um, so yeah, going back to atomic structures, can anyone tell me what are these? These are something of carbon. Anyone? Those who, the chats are available as well. Can anyone tell me they are? Brilliant. Well done. So isotopes of carbon. Good work. Now, you may ask, what is an isotope? Well, an isotope is simply different. They have, they're the same elements because they're the same atomic number. Well done, that student as well. Different mass numbers due to different numbers of Jimmy neutron. Yeah, I don't know I don't know. Very poor attempt of a reference there. Okay, different mass numbers is due to a different number of neutrons. Okay, however, please write down they have the same number of electrons and same number of protons. Okay. If you remember the atomic number, that gives a sort of identity, doesn't it, of the element? And crucially, atomic number equals the number of protons. But these are both the same. Now, another potential question would be, explain why these carbon isotopes, explain why these carbon isotopes react similarly. They share the same chemical properties. Well, can anyone tell me, why do you think these carbon isotopes, or any isotope for the matter, react similarly? They have the same, more or less the same chemical properties. Can anyone tell me? And also, can you guys hear me? Is it clear? Please let me know if there's any issues with the stream going forward in this hour. But yeah, explain why these carbon isotopes react similarly. But there's one subatomic particle we're more focused on. COL, and that user, I can't really pronounce your username, but can you tell me why these carbon isotopes react similarly? Okay, 5, 4, 3, 2, 1. It's due to the fact that they have the same number of electrons. They have a similar electronic configuration. So that's why they react similarly. Because at the end of the day, when things react, they more or less lose electrons or gain electrons. And that's what sort of defines a reaction, really, in terms of electrons, in terms of redox. And so I suppose that it makes sense. So same number of electrons and a similar electronic configuration and stuff. Okay, so basics on atomic structure, but sometimes you'd be asked to work out the relative molecular mass or relative atomic mass. Now, this is fairly simple. So I'm going to find a good question now. So let's find one GCSE. All right, cool. So we have chlorine. So there's two types of chlorine isotopes. You've got 35 chlorine and 37 chlorine. And they have an percentage abundance of 75%. And of course, 100 minus 75 give you 25%. So they've got this sort of 3-to-1 ratio, don't they? Okay. Yeah, 25. Yeah, 3-to-1 ratio. And you'd be asked to simply calculate the relative atomic mass. So how would you approach this question? So generally, it's straightforward. So step one is just assemble brackets. Assemble the following, really. So you've got the mass times the abundance plus, let's say, mass 1 and abundance 1 because of this particular isotope, mass 2 and abundance 2 for this isotope over the total abundance. Now, sometimes I'm not sure if I've seen any particular question in which they've not given the other percentage. Sometimes they do that. Okay, just ensure you have the total percentage. So if this happens to be 10, the denominator would be 85. Okay, so I've seen, maybe it's an A-level question, but I've seen that before. Okay, so I'm going to now substitute these values. So mass would simply be 35 times 75 and get rid of the percentage plus 37 times 25 over the total, and of course the total is 100. And can someone calculate this, please? What would the relative atomic mass of this chlorine be? Is it 35.5? Yeah, good stuff. Correct. Indeed. So assemble the brackets in the following, and yes, rather simple question. In A-level chemistry, they sort of throw you off guard and make something algebraic. They could say, what could the mass of this particular chlorine or strontium element B. They could say X. They could tell you the relative atomic mass, so you have to work backwards. But I'm sure you guys are good at algebra, so I've got nothing to worry about. Okay, so atomic structure done, just basic concepts. Let's deal with structure and bonding. Now, I'm going to leave it to the audience then. Can anyone just write down 3 ionic compounds, please? And make sure, um, based on, of course, the group they're in, make sure there's a correct ratio of atoms to the cation and the anion, as in this would be incorrect, wouldn't it? The reason why this is incorrect is because sodium has +1 charge and chlorine has -1, so naturally it's NaCl. Okay? Yep. So yeah, we already got one NaCl. Can anyone give me any others? Any other sorts of ionic compounds? Let's see the chat. Yep, that's a good one. NaF, NaCl, yep. Calcium oxide, or even further, you could do calcium and you do calcium hydroxide. So can anyone tell me why I've written CaOH in brackets and 2 subscript, please? Anyone tell me? What what's so special about this hydroxide ion? It's because it has an OH minus charge, like collectively has an OH minus charge, and calcium has +2. So you have to sort of double it. If you think about it, let's put it here, +2. Yes, well done, that student. +2 and then minus and -1. So it reaches equilibrium, reaches balance. So that's why. Brilliant. So yes, well done to neutralize the charge. Very good. Matt Potet 17, whoever that is. Well done to you. Now, yeah, so they're all ionic compounds. Now, please approach this SBE format, and I'll explain in one moment what that means. Now, ionic compounds have high melting points. Slash boiling points. And in these questions, it's all modeled. That's why chemistry is really good because you have model answers. It's not as harsh, the mark schemes, as opposed to biology, is it? So here's one of the modeled answers I go for. So the reasoning to why they have a high melting point and a high boiling point is due to the following. So quickly, the structure of ionic compounds is the following. It's got a giant lattice structure. That cubic, sorry, looking structure that has big chloride ions represented by minus, because it's obviously got a minus charge, and also a smaller sodium charge, sodium atoms with a positive charge, okay? And so it's got a giant lattice structure. Number two, sorry, bonding. Now, it's important to use the word strong, okay? And mention they have strong ionic bonds, but also mention the following. Mention they have strong electrostatic forces of attraction. Now, this is not good enough because mark schemes require this sort of specific phrasing. They require between. Okay? So my teacher back in the day for A level stressed this word between. And of course, it's between the oppositely charged ions. Okay? So it's between the oppositely charged ions because, of course, sodium is positive and it's got that electrostatic attraction with chlorine. Okay? And then energy. So the E is in reference to energy. Now I'm going to leave it to the audience now to answer this. Would a lot of energy be required or little energy be required to overcome these forces? What does logic tell you? Okay, so you see what the chat is saying? Yes, a lot of energy. Well done there. That's it. So a lot of energy is required to overcome these. In a moment, we'll go over simple molecules, and it would mean little energy is required. So a lot of energy in this case, because it's got strong ionic bonds. So yeah, brilliant. A lot of energy is required to overcome these forces. Good work, guys. And then, of course, we've got a good question here. So 5 marks worth of questions here. Good luck. And if you can sort of upload them in the chat, that would be fantastic. So I will give you, let's say, 3 minutes to answer this. Good luck. Yep, some really good answers here. Being a full outer shell, brilliant. Also make reference to the 288, all of that electronic configuration. That's what you guys learn. Although it's truly at A level, you'll learn that it's truly cap, isn't it? That was my attempt of drawing a cap. Anyways, yep, some really good answers then. So Mark scheme shares the following: Lithium changes from 2,1 to 2. There's a full outer shell as a result. Or you can mention the fact that it loses one electron. Yeah, it loses one electron, and oxygen gains 2 electrons. Of course, 2 molecules is required for that. And here, look, it's got strong electrostatic force of attraction between the oppositely charged ions, and a lot of energy is required to break them. Of course, you can't make any reference to things called chemical error equals 0. If you make any remarks to the following covalent bonds, intermolecular forces, you just be scored 0, be penalized. Okay. And also notice you'd be wasting time if you said it had a giant structure. The reason why I include the SBE format is just in case they say explain why lithium oxide is a solid at room temperature. So it's sort of implied, isn't it? But and also in some questions they may ask refer to structure and bonding. But yeah, just be careful if stuff's mentioned in the question, most likely won't be a mark. Okay. So yeah, brilliant. And the next one, like I was mentioning, was simple molecules. So these include the likes of sodium, not sodium, apologies, that's a metal. I was actually going to draw ammonia. Okay, so ammonia, chlorides, all these diatomic molecules, water, these are all simple. Okay, so just like compare the meerkat.com, it just says simple, doesn't it? Okay, the structure is simple molecules. And then the bonding, and this is where you can't say covalent bonding, okay? Although that it shares electrons, you don't make mention that remark. You mention it has weak IMF. Now there's a reason why I use abbreviations in my lessons. Of course, I'm going to tell you what the abbreviation stands for, but it makes things. It just stays in your head, doesn't it? In your hippocampi, in your memory storage. And the IMF stands for the following: intermolecular forces of attraction. You can go a bit further. And of course, energy. Little energy is required to break these forces, overcome these forces of attraction. So yeah, that's simple molecules. Now, on the other side of the river, you have giant molecules, okay? And these include silicon dioxide. That's one sort of chief example. And the structure you'd say would be the following. It's a giant molecule. The bonding includes, well, what would you mention for bonding would be the following. It has strong covalent bonds. Notice I've underlined it, so that illustrates its significance, that phrase, okay? Strong covalent bonds. And then energy, well, it's the same all, isn't it? The SBE format. A lot of energy is required. Okay? A lot of energy is required to overcome these forces. Brilliant. Like I mentioned, there could be cues in the question. They could ask the following: explain why chlorine is room temperature and why sodium chloride. No, it's the other way around. Why is chlorine a gas at room temperature in comparison to sodium chloride solid state at room temperature? These things could occur in questions, could be alluded to, hinted at. Okay. Now, can anyone tell me any carbon allotropes? or the way that carbon can be manipulated to make a bunch of other things. I'll give you a clue. One of them is used in tennis rackets. A lot of you viewers, I imagine you guys play tennis. Yes, that's one. Well done. You have graphite, and also you have another one called graphene, which we'll explore in a moment. Any others, guys? Diamond, exactly. You have diamond. What else do you guys have? Um, fullerene. You have fullerenes as well. Now, can anyone tell me any features about graphite in particular? Like how many carbons does one carbon bond to in graphite? Can anyone tell me why is that so significant? Wait for the lag. Anyone? Just check the chat. Yes. So basically, let's make this a bit. Let's erase all of this. Let's talk about graphite first. Now, graphite is in layers, okay, and that gives rise to its slippery nature because the layers can slide over each other. Quite different to an alloy, because the alloy have irregular layers and have irregular sized metal atoms. They're in an irregular arrangement that gives rise to no sliding of layers. So that's why they're quite stable and hard, non-slippery in essence. And fantastic. One student's mentioned that it has a giant covalent structure. Brilliant. Giant covalent. Brilliant. But in terms of the bonding, one carbon bonds to three others. Okay? Yeah. So one carbon is bonded to three other carbons, and this gives rise to delocalized electrons. So basically, one of the electrons will be delocalized. But of course, if you've got loads of carbons doing the same thing, and in reference to the hexagonal layers, then you will collectively have delocalized electrons. And can anyone tell me why is that so significant? Why is that so important? Yeah, fantastic. Yeah, it's delocalized electrons give rise to the conductance of electricity. They can conduct electricity. Okay, brilliant, good stuff. Another thing is, of course, it has strong covalent bonds. Just mentioned that as well. And of course, the bonding is covalent, so it has strong covalent bonds. Now, I forgot with the ionic bonding. I forgot to mention that um, the reason why ionic bonding or ionic compounds can conduct electricity. Can anyone tell me how can they conduct electricity? Because the ions are free to move. So the ions are free to move. This means that they can conduct electricity. They can, carry charge. But that's only in two circumstances. Can anyone tell me? Can anyone tell me what two states can ionic compounds conduct electricity in? Anyone? So the two states are the following: one and two, molten and in aqueous solution. Okay, good stuff. Wojito, good answer. Well done. And that's simply because the ions are free to move. There's a good question where they asked, explain why solid zinc chloride cannot undergo electrolysis. Of course, with electrolysis, you're using electricity, aren't you, to break down, split ionic compounds. But the reason why you couldn't use solid zinc chloride is simply the ions are not free to move. So a bit of reverse logic that could be applied in some particular questions. Okay, ions are free to move and they can conduct electricity. Good stuff. Would you like to have a go at this question then? So graphite is a naturally occurring form of carbon. Explain why graphite is soft and can conduct electricity. Please make reference to structure and bonding in your answer. So I shall give you 5 minutes for this question. Yeah, so 5 marks. Write an answer there. And so basically, we're talking about graphite. My spiel on ionic compounds, we'll do ionic compounds, so like sodium chloride, potassium chloride, that's to do with ionic compounds. Graphite's a bit different. It's part of a carbon allotrope. Yep. So good reference to the fact that it has delocalized electrons because of the nature of the bonding. It has um, layers, it has stronger covalent bonds, it has delocalized electrons, and the electrons can conduct electricity. They can move. Okay, the layers and the weak forces between the layers that gives rise to the slippery nature. Okay, and they can slide. The second half refers to the actual nature of the bonds. So each carbon can bond to three other carbons and collectively make three covalent bonds. And of course, there's a delocalized electron among the bonds per carbon, and electrons can flow and move. Okay, to allow electricity. So if you mentioned 5 of these points, you'd be awarded 5 out of 5. But of course, there's an extra N6 here. Okay. So graphite is a naturally occurring form of carbon. We haven't got enough time to go over diamonds, so I'm going to quickly rush that, I'm afraid. But we're going to make a start with calorimetry. Okay, so how do you calculate enthalpy change? You may ask. Okay, the sort of energy change. So I'm gonna talk about the combustion calorimetry sort of calculation first. We deal with the first type of formula, and of course it's Q equal mc delta T. Now remind me, I'm not sure if you guys have these formulas, because obviously with biology, well, I mean, you don't have really any formulas. They provide it in the test. Do you guys get given formulas? But if not, you guys, I suppose, need to have this mental image. So Q equals energy release. And it's named after someone that happened to be, used to live across my school back in Manchester. And there's a pub named after him, and it's JP Joules. So joules is your units, okay? And delta T, delta, as you know in maths, delta Y over delta X is in reference to change. So that's change in temperature. Initial minus final, other way around, final minus initial. C is your specific heat capacity. And typically, based on this question here, they'll give it in that format. Sometimes I see it in kilojoules, but it's 4.2 joules per kg. We'll check that. Nope. Per grams Celsius. Okay? Per Celsius. Or if you want to go all maths about it, you can have this -1 and Celsius -1. But anyways, so that's a specific heat capacity. And M is in reference to the mass of surroundings. Okay? Mass of surroundings. Probably wondering, what do I mean by mass of surroundings? So remember, we had like a water bath, didn't we? So you would simply measure the water bath's mass and apply it to this formula, not the sort of energy released by this particular fuel. So let's say this is go for a propanol, okay, which has an MR of 60. Okay, so we're more concerned with the water in this case because it's the mass of the surroundings. Okay, so I'm going to find some questions now. Let's use actual values. So let's get propanol using a combustion equation. Practical. Really good ones there. Okay, I suppose I can make it up, can't I? So let's say, I mean, is this really hard? You can just plug in values at the end of the day. The second thing you'd do to work out the enthalpy change is enthalpy equals the energy, which was Q, over the moles reacted. And this is when you concern propanol, okay? So how do you calculate moles? How do you make this calculation? Now, the next thing I'm going to teach you guys is this formula, okay? Mass equals mR times moles, or Mr. Moles. In mass notation, the dot is in reference to multiplication, and mR is obviously the total number of atomic masses of the particular elements, constituent elements in a compound, or if it's the element itself. So Mr. Moles. Now, I'm not a fan of pyramids, okay? I think every student should have an algebraic mind, and just because you're reliant on covering something and then, oh, that's what it is. I don't think that's the way forward. So please, mass equals mR times moles. So you would simply do mass over mR, and that should equate to moles. So if this had an mR of 60 and this is 1 gram, the moles would be the following. It'd be 1 over 60, okay, based on that formula. And whatever that energy is, if you multiply all these variables together, you get the energy release, you put that on top, okay? But can anyone tell me what a positive enthalpy sign suggests and what does a negative enthalpy value suggest? Anyone? Positive enthalpy value and a negative enthalpy value. Can anyone tell me what combustion is? A combustion is a brilliant. So very good answer there. So if you have a negative enthalpy value, it's exothermic. Okay. How do you know it's exothermic? It's when you have an increased temperature rise. Okay. So let's say something increased from 20 degrees to 180. We know that's exothermic. If you know that it's endothermic, you would have a temperature decrease. So this would be presented by a positive value. That would be endothermic. Negative is exothermic and positive is endothermic. Fantastic. Good stuff, guys. Okay. Now I have a question. Now this is a bit different. It's neutralization. However, they've sort of broken it down a bit, and they want you to refer to algebra in this particular question. So question A. Oh, let's actually read it. Student uses apparatus to record the maximum temperature in this reaction between solutions of NaCl and NaOH. Of course, this is a neutralization reaction. We have the following values, ingredients, and they're asking you to name a suitable piece of apparatus to add 25 centimeters cube of solution to the beaker. Has anyone got any idea? What's the answer to this? What would you use? Yep. So you could use a pipette. You could use a measuring cylinder. Measuring cylinder was the one they went for, but in additional guidance, they mentioned burette, pipette, syringe, so on and so forth. Okay. Now, can you guys calculate this? This 4 marker? And also, could you suggest a reason why the value was lower? And also, continue on and calculate the enthalpy change. Yeah, I'll write down the formula as well. Q equals MC delta T. Anyone? So they're asking you to sort of rearrange this formula. So you got this many joules, the mass. Oh, it's a good one actually. It has a mass. The theoretical mass reached by the mixture is 50. So it's based on the density of water, isn't it? The density of water is 1 was it mass? So 1 grams per centimeters cubed. So based on that sort of assumption. So we got 50 times 4.2 times the energy change, the temperature change, and the temperature change is simply, let's look at the calculation. Oh yes, so yeah, I thought they were asking the maximum temperature change, but they haven't. Oh, temperature change, wasn't it? And then you simply do this over 50 times 4.2. And what did you guys get? What value do you guys get? Anyone? Yeah, 13.7. Well done. No, 13.7. Brilliant. I believe my question got cut up, but basically you had to use an algebraic equation to sort of work out if that was a change, it would be x minus, your initial temperature, and that would have been 13.7. But I think the question got cut up at the beginning, so apologies for that. But can anyone tell me, give a reason why the temperature recorded by the student is lower than the theoretical um, and maximum temperature calculated? Can anyone think of any reasonings, explanation why that is the case? Nope, not quite. Yep, so the heat sort of escaped to the environment, isn't it? To the surroundings. At the end of the day, it's an exothermic reaction that occurs. That's why. And guys, could you finish off that question then? Calculate the molar enthalpy change. Yep, they could have used the lid. That's a way of improving. Fantastic. Is that Abdi? Brilliant. And this is pretty straightforward, like I mentioned. Enthalpy equals the energy, which was this, 2880 joules, over that many moles of HCl. Because it's the same, isn't it? If you think about it, NaCl and HCl, they have a 1-to-1 ratio, don't they? They're the same number of moles. It doesn't matter. So neutralization occurs, and then can anyone tell me the value? And can anyone tell me the sign? And I don't mean trigonometry. And look, someone mentioned a remark that was in kg, so that's another thing as well. So what would you do towards the end? Basically, you'd get 57600 joules mole minus one. It's just another way of writing it, and then you divide it by 1,000, giving you 57.6. But I've forgotten something, guys. What was the sign? Because it was a temperature increase. What would the sign be? Anyone? What sign am I looking for? It would be a negative sign because it is exothermic. That's why. Yeah, brilliant. So that was the answer. The temperature change was 13.7. Suggests the reason why, yep, thermal energy gets lost to the surroundings, so on and so forth. Brilliant. Now, the next segment I think I want to focus on, because I am running out of time, I have to cross this on out, organic test, is organic chemistry. Okay? Um, so, I suppose you can learn a few things if you haven't done organic chemistry. Can anyone tell me what two elements basically make up organic chemistry? Anyone? There's those who have communicated already. Can you tell me what two compounds, top two elements make up most of organic chemistry? No, I shall write it down. It's hydrocarbons. These include compounds only contain carbon and hydrogen. Okay, that word only is important. I've seen it in mark schemes. And there's two types you learn at IGCSE double award. You have alkanes, which are regarded as saturated hydrocarbons, and you have alkenes. Okay, students can get confused with the spelling anes and enes, and these are unsaturated hydrocarbons. And unsaturated hydrocarbons, they deal with, they're characterized with carbon double bond. Okay, whereas alkanes have a carbon single bond. Okay, and we're going to explore some other sort of differences as well. Now, alkanes and alkenes, and in fact, naming in general, nomenclature, they all have something called a stem. They share a same stem, but the ending's a bit different. So that's what we're going to talk about in one moment, naming organic structures. So let's say number of carbon and let's say the stem or prefix. And then you could add an ane, an ene to it. or sometimes you're making an alcohol add an ol. So let's start off with 1 carbon, 2 carbon, 3 carbon, 4, 5, and 6. If you have 1 carbon, you have the stem meth, like methamphetamine, meth. Methane, that would be an alkane. It has 1 carbon. And then we wouldn't, it's non-applicable for something to be called methane because, a carbon, an alkene has a carbon double bond. And put simply, if you only have 1 carbon, how are you going to have a carbon double bond, So it's not non-applicable. And then the stem for 2 carbons will be eth. It will be ethane. However, yes, you can make ethene here. 3 carbons, you have prop. Okay, you got propane, like in the previous question, propane gas, and then you got propene. 4 carbons, it's bute, so it's going to be butane, and then butene. And of course, you want to make an alcohol, you can make methanol, you can make ethanol, you can make propanol, butanol, all having 1, 2, 3, 4, 1, 2, 3, 4 carbons respectively, in that order of that sentence I've just talked about. Okay, question number 5 and 5 carbons would make pent, like a pentagon. And then you get pentane, and you get pentene. And 6 would be hex. So hexane and hexene. Next slide we'll deal with drawing organic structures. And this is quite straightforward as well. So if I were to draw methane, it has 1 carbon and it has 4 hydrogens. If I were to draw, let's say, propane, 3 carbons and 8 hydrogens. Now, let's make an alkene, ethene. Now notice this. 1 carbon can bond to 1, 2, 3, 4 bonds, okay? So let's say A, B, C, D. And it's the same case with this particular organic structure as well. Propane, that is. So if you look at this carbon, it can bond to A, B, C, D. That's 4 bonds. So that's for this carbon in particular, carbon 1. For carbon 2, we have A, B, C, D as 4 as well. The third carbon at the end, you have A, B, C, D. Okay, there's 4 carbons. Now look at this alkene structure, this unsaturated hydrocarbon. Carbon double bond, it has 2 bonds, doesn't it? So carbon here, A, B, and this other one, C, D. And if you look at this other carbon, you have A, B, C, D. So it's really important, it's really worthwhile to draw these compounds and count that a carbon can only bond to 4. So carbon only bonds to 4 atoms. And of course, with a double bond, you've got a minus 2 bonds from that. Okay? We're going to now end it with a test for alkenes because I need to go somewhere. Does anyone know how we test for alkenes? Respond in the chat. These are the final viewers of the stream. If you could let me know. the test relevant for testing for alkenes presence? Anyone? It's a halogen. No worries. It's bromine. You could add bromine water. And naturally, bromine is orange, okay? And if you add alkenes to it, it goes from orange to colorless. That's if you have an alkene, whether it's ethene, propene, butene. But from an alkane point of view, um, there's no visible change. It remains orange. And that's that. And that's all I've got time for, folks. Thanks for listening. There'll be more chemistry content. This is the first one on this channel. I'll make some more shorts. I'm going to make some empirical formula uh, calculations and whatnot. I just realised I didn't put a second S with colourless, didn't I? It's meant to be colourless. Yep. So, all in all, yeah, thanks for listening. There'll be more content on this channel, better quality as well. I'm dedicating the summer holidays to um, making these videos, making more interactive videos, making a website maybe as well. So there's a lot of things in the pipeline. But yeah, all the best. Take care. Good luck for Monday, and I'll see you in the next episode. Ta, bye.